Good morning, everybody. How was your weekend? Long? Work? Yeah, sounds pretty normal. Let's see. For this class, important information. Tomorrow's lab. Tomorrow's lab is lab 4. It's projectile motion. We're going to talk about it today. It's the only lab that we require you to wear safety goggles in, for reasons that will become apparent tomorrow. So if you have a favorite set of goggles, say from chemistry, okay, that you want to bring, great. If you have shop glasses that are impact resistant, that you use all the time, great, bring those. If you don't have anything to bring, you don't have to go buy anything. We have a bin of goggles, orphaned goggles from previous years that we sanitize, and they will be available for you. Okay, so just realize that if you want to bring your own, bring your own. If you don't, we will have goggles for you, and we'll require you to wear them during the lab tomorrow. Chapter 3 homework is due this Saturday. I'm done with chapter 3. You should be too soon, because chapter 4 is here, right? And chapter 4 is a big one. Let's see, what else do I have to remind you of? I think that might have been it. I might remember something along the way, but we'll see. One of these days I'll actually write this stuff down and I'll be a better teacher. Here's the roll sheet, okay? I believe this is the last week that we will see the roll sheet, because after this week I do the census, and then I don't care about taking roll. I care about you, but I don't take the roll. It's just piece of paperwork I don't want to do. All right, so what have we covered so far? We have 3 equations. I call them the 3 equations, right? The 3 equations of kinematics. And we've learned about vectors, specifically magnitude, direction, and that we can break vectors up into their component parts. We're going to bring this all together today in the context of projectile motion. Okay, so this is going to be, so back when we did chapter 2, we defined free fall as something. Do you remember what the definition of free fall was? Only gravity is acting on the object, right? We ignore air resistance. If the ball hits the table, once it hits the table, is it in free fall? No, because it's hit the table, right? Gravity can only affect things as long as nothing else is touching the object. So we're going to extend that definition. It's still the same definition, but any projectile is anything that is experiencing gravity only. So something going straight up and down works, something that gets dropped works, and anything that gets thrown sideways also qualifies for that. The big problem in chapter 4 is now we have both horizontal. Remember in chapter 2 we did horizontal problems like with cars and things, but we also have a vertical problem that we are going to put together. So we've got to tease that out and deal with the different accelerations in those different directions. So let me just show you something about these kinematic equations, because I mean they have velocities and accelerations and everything in them. And so that means that these are vector equations, and vectors allow us to sort of compress a lot of information into a little space. So let's see. We had, I think I called this one the first kinematic equation, right? We wrote it down like that in chapter 2. But really, the final velocity is a vector. The initial velocity is a vector. The acceleration is a vector. What's not a vector? Time. We just consider that a scalar, right? So what this means is we can write down this equation, and it's really 3 equations. Why would it be 3 equations? The clue is René Descartes. No, the Cartesian coordinate system. Oh, ho, ho. We can split it up into components, which means that we can write this equation as v sub x equals v naught x plus ax times t. Now, is it a different equation? No, we've just kind of written it with different labels, right? And you can see I've removed the vector signs off the top. That's because those x's are sitting down there. What do you think those x's are trying to tell you? It's the x component, right? Okay. So what's the second equation going to be? It's going to be the same thing with a bunch of y's on it, right? And then what's the third equation going to be? I'm not going to write it down. It would be the z direction. Now, in this class, we're going to stick to just two-dimensional x and y. Chapter 4 is two-dimensional motion, right? So we're not going to do things in the third dimension. We'll save that for Physics 4b mostly. But I can do this with all of these kinematic equations. Now, the second one is a little bit tricky because we wrote the second one. How did the second equation start? Do you remember? It was delta, and now we run into the problem, right? X, Y, Z. Like, how do we do this in a generic sense? Now, unfortunately, physicists don't agree on this. So you'll see a few different symbologies. The one I learned was delta R. And as soon as you use R, everybody thinks radius. This is not a radius. In physics, R is a generic position vector. So sometimes you'll see delta R. A lot of times across the world, outside the United States, you'll see delta S, where S is just, again, some sort of generic direction. It can mean X, Y, or Z. It kind of depends on the context, right? And then I've got my V naught t plus 1/2 a t squared. There's the vector version of it. But again, this splits up into a delta x equals v naught xt plus 1/2 ax t squared, a delta y, v naught it, that's 1/2 ay t squared, and could do a z1, right? Third one, v final equals v initial plus a delta, we'll just use s, okay? And again, right, we can split this into its x and y pieces, where we put the x's on everything that's got a vector component. We put the y's on it as well. Now, I mean, for a Tuesday morning at 8 o'clock, right, this is probably a lot of math to be throwing at your face, right? But I hope that you see here, oh, I did that all wrong, didn't I? Thank you. Still, it's a Tuesday morning at 8 o'clock. Squared, 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 thank you. V naught x squared plus 2, boy, I really messed that up, didn't I? Ax delta x. And then this would be v naught y squared plus 2ay delta y. There we go. Thank you. Panicked looks out there. But what I hope you take from this, right, is even though I have written 1, 2, 3, plus 9 equations on the screen, that there's really only 3 up there. It's just a matter of like switching the symbols around to catch the meaning of what we're doing, to help our brains sort out, are we dealing with the horizontal direction or are we dealing with the vertical direction, right? And this is laying out sort of a step-by-step process where we're going to have to break up our motion into these component parts. We'll use that vector stuff that we learned. Another thing to mention about this, well, I'll get to that in a second. Let's talk about specifically projectile motion and the limitations that we are going to put on ourselves in this chapter. We're going to try to simplify, take baby steps, right? Not get completely overwhelmed with things like air drag and all that sort of stuff. So for the context of chapter 4, projectile motion means very specifically that the acceleration in the y direction will be negative g. And what's g? Gravity. It's 9.8 meters per second squared. It's not just gravity, it's the acceleration that gravity gives to all objects. And notice, G is just a number. G itself has no direction. Little g is not a vector. It's just a scalar. Do you see how I wrote AY equals negative g? So which way have I defined as being positive? Up, right? Anything that's moving up, anything that's being accelerated up, all right, we have a positive direction. Anything that is moving down with velocity, right, down, would have a negative sign. If it displaces down, I got to put a negative sign on it. These are important. But little g itself is not a negative number. Little g is just a symbol that means 9.8 meters per second squared, right? It's up to us to put the sign on it. The other thing that we are going to assume is that our acceleration in the x direction is going to be 0. So that means that if I throw a ball across the room, does its vertical velocity change as it goes? Yeah, because it's moving up and down like this, right? It's also moving sideways, but it's moving up and down. And does it come to a stop at the top? Sure does, and then it speeds, right? So it slows down and then speeds up. But heading across the room, right, we're going to assume that its horizontal speed stays exactly the same. We're not going to speed it up. We're not going to slow it down in the sideways motion. Now, in truth, this is not what high-speed projectiles do. The faster a projectile goes, the more pronounced this effect is. But like hitting a golf ball can tend to have the trajectory be more like this, right? Where it sails almost like has lift. That's what all those dimples are for, okay? Gives it lift, and then at a certain point, air resistance kind of takes over and it'll fall straight down, which is great for golf because you want your ball to go where you plan on it, right? So you can count on things like this. But in the case of baseball, when they're trying to throw curveballs and things like that, you need the air resistance in order for a slider to be a slider and for a curveball to be a curveball. It's just, if you play baseball in a vacuum, then everything is just a straight fastball. Okay? So those are important, but we are going to ignore those things right now because those are pretty complicated things. All right, so if these are sort of our assumptions and the rules that we're going to go by for chapter 4, then what do our equations look like? Let me write them down again real fast in their component forms. You don't have to write all of these down, because there's going to be some ones that fall out that are going to be really important. I want you to see what happens here. Where am I? T plus 1/2 ax t squared delta y t t squared. I think I'm writing these down correctly this time. This is an x, v naught x squared plus 2ax delta x. And same thing with y's on it. Okay. There we go. I've written down our toolbox kinematic equations in both the x and y directions. But notice when we do projectile motion, ax is equal to what? 0 is a nice number, isn't it? Yeah. Because what happens when I put in ax equals 0? That one goes away, doesn't it? And that term, right? Now, take a look at that statement right there. What does it say? Well, yeah, right? If there's no acceleration, if there's no change in velocity, what do you expect the beginning and the ending to be? You can tell that this is a mathematical statement. It's true, but not useful. Sorry, all you math majors out there. I do like mathematicians, I just don't like math. Okay, same thing for this one. Only the horror of the square root creeps in, right? Okay, but again, not useful at all, right? True, but can't help us in our problem solving. In fact, what's the only thing that survives? It's just the delta x equals v naught x times t, isn't it? That's the only thing that comes out of the x direction that's of any use to us when we are considering projectile motion, which is already kind of like a nice simplification, isn't it? Okay. In the y direction, though, we do have all of these things, don't we? Okay. So let me bring this one up over here, okay? Because what's in the box right there is what I consider the toolbox to be for chapter 4. Now, chapter 4 is going to have a lot of equations in it in your book. And you're going to see lots of math. But really, if you have these 4 equations, you're golden. You can solve anything. Are they any different than what we encountered in chapter 2? I mean, yes and no, but not really. They're the same 3. And then that 4th x1 gets tacked on because of our special things for acceleration in the x direction. How do you know? Let's say on the exam, for example. You're going to have a bunch of problems on the exam. They're all going to be mixed together. You're not going to know which chapter it's coming from, blah, blah, blah. How do you know if it's like a chapter 2 horizontal problem where there could be horizontal acceleration versus, say, a chapter 4 problem where there's no horizontal acceleration? How do you tell the difference? If they're talking about an object speeding up and slowing down in a horizontal direction, is that projectile motion? No, right? That's a train speeding up or slowing down. That's a car, it's a motorcycle, right? It's a bullet or something, right? But if they're talking about something being launched or thrown or dropped, those are key words that are cluing you into now we're dealing with projectile motion. So it's all about context, right? It's all about being able to identify. And I'll tell it to you straight. Your homework is probably not enough to do really well on the exam. You want to look at those end of chapter problems. Don't even try to solve them, but try to identify and learn sort of the phrasing and the words that are used, right, in chapter 4 problems compared to chapter 2 problems, and be able to identify. Like, build yourself some flashcards and just copy paste some of the problems on there, and then, like, you know, test yourself. Is this chapter 2 problem? Is this chapter 4 problem? How do I know, right? It's not enough to just sort of say, I'm going to do math. You need to learn this context and all that sort of stuff that is surrounding it. Okay, so that toolbox right there is what I consider to be the be-all, end-all of the tools we're going to use. I'm going to write it up here on the abomination, just so I can refer to it, v naught y, during class, so I don't have to keep coming back to this slide. Let's see if I can do this right. You know how hard it is to talk and write down math at the same time? I've been doing this for years and I still can't. Did I get that right? Yeah, okay. V y squared v naught y squared plus 2ay delta y. And then delta x, v naught x times 2. There we go. Did I get it right that time? I think I did. All right. Those of you that have been looking at the book, good job, may have noticed, get a different color, that they write them down differently in this chapter. In fact, I think your book, I think they write the second one. I'd have to go back and check. Apparently, I have not read the book. They'll write delta y, well, they might write y equals y naught plus something. Is that what they do? Yeah. Oh, geez. Okay. So they do like y final minus y naught. Okay, y final, y initial. Do they do the minus on this side? Yeah. Okay. It's all the same in my brain. Equals v naught sine theta t minus 1/2 gt squared. What just happened? First of all, what's this? It's just delta y, right? Let's ignore this for a second. What happened over here? they went ahead, like it says on my screen, AY is equal to minus G, right? So perfectly good substitution, right? Here, and we're going to talk about this in a second, they've inserted the vertical component of velocity. The problem is this, okay? If you were to look at this blue equation I've written down right here, as a total noob to physics, does this blue one look the same as this black one? Not really, right? And so your brain immediately goes, oh, it's another equation. It's different. It's not, right? It's still the same thing we did in chapter 2. And part of your learning process is to be able to read between the lines. So even though your book kind of does this, I don't like it because I don't like having to reinvent the wheel, right? What I like is to just take what I've already learned and be able to apply it to any situation. The toolbox I've given you up here can be applied to any projectile motion problem and won't hard lock you into acceleration being a certain direction, all that kind of stuff. See, I know what's coming. And I'm trying to prepare you for chapters 5 and 6 and 7 and 8, which are some very hard ones, right? And so the more I can help your brain start recognizing these patterns, the better off we're going to be. So even though your book may have different looking equations, they are the same thing. All right, so when it comes to these vectors, right? Let's do an example, okay? And in this example, I'm going to do the visualization. We're going to talk about strategy. We're going to do the math, although I'm probably going to skip a bunch of algebra. And then we'll do a check. Okay, so this is the same problem-solving method I had in chapter 2, right? I'm just going to apply it now to the chapter 4 case. Because we have a toolbox that specifically calls out the y direction and the x direction, we must work in just x or just y directions. We can't do it simultaneously. We must break up our motion into pure x and to pure y. The reason being is that anything that's doing projectile motion, whether it's launched horizontally, right, or dropped, or thrown through the air, okay, the acceleration is which way? Down. What's accelerating the ball? Gravity. And gravity only acts vertically. Does gravity act horizontally? No. Okay? So if gravity only acts vertically, the horizontal motion is unaffected by it. And so we have to break it up. Remember that these toolbox equations can work for constant acceleration. And that acceleration is different in the vertical than it is for the horizontal. So we have to break them up. How do we do that? Let me show you. Give me an object that you would like to see thrown or launched off of a cliff. Cannonball. Cannonball? Boring. Been done before. Because of the moral and ethical considerations with launching people off of cliffs, we won't go there. Although there are certain public servants, can we call them that, that I would like to see launched right now. A potato, a Ford Bronco? I'm game. I'm game. Does anybody know what a Ford Bronco is? It's a car. It's a vehicle. It's a little bit like an SUV or a truck. The older ones looked a little bit more like Jeeps. Okay, so like a 4x4 type vehicle. Let's see here. Has this Ford Bronco been involved in some sort of stunt for a major motion picture? Yes or no? No? Okay, so in that case, this Ford Bronco is just being launched for some reason. The Science and Engineering Club's gotten their hands on a Ford Bronco, and they want to see it launched. True story. We had a new science building built at my alma mater, and I was undergrad at the time, and we decided to christen to open the new science building that we were going to do some experiments. And one of our experiments was dropping apples off of the roof. We found a bunch of Apple II Plus and Apple IIe computers from the 1980s, and we plugged them in, duct taped their monitors to them, and threw them over the edge while running Oregon Trail, because we hated that game, because we always died of dysentery, okay? And threw them out the building, got slow-mo footage, and used it in all the physics classes to teach people about projectile motion. So yeah, we dropped apples off the building. Okay, so we got Fort Bronco. Okay, so what's going on here? So we've got a cliff, and we're going to launch this cliff into the ocean, Millerton Lake, I don't care, body of water, okay? What's that, Shaver Lake? Yeah, okay, because Shaver's pretty, well, but we don't want to pollute the place. Okay, so this will all be done environmentally responsibly and all that kind of stuff. Okay, so let's say that we rig it up so that this Ford Bronco gets launched at 40 meters per second at an angle of 50 degrees. So what is that? What have I given you? It's a vector. Specifically, what vector is it, though? What are our choices here? It could be a velocity, it could be a displacement, it could be acceleration, it could be, what is it? It's a velocity vector. How do you know that? Because it's meters per second, right? The units are a dead giveaway. Okay? So this is a velocity vector. Is it the velocity in the y direction? It's x and y. And how do you know? It's at an angle. Because if it was x, what would the angle be? 0, wouldn't it? If it was y, what would the angle be? 90, right? So this is happening in both. This goes beyond chapter 2, right? We've got to use our chapter 3 skills of breaking up vectors into their component parts. And so before I do even anything else, before I start to kind of visualize and make a list and do any of that kind of stuff, I am going to break my velocity. If you're given an initial velocity and it's at some angle, go find the components. You are going to need them at some point. Okay? So how do we find the components of this vector? So it has x and y pieces, doesn't it? We're going to break it up into those pieces. I'm going to come over here, and I'm just going to draw this vector, right? Just off to the side to make sure I get this done right, okay? And there's going to be an x piece. This is going to be like my v naught x. And then there's going to be a y piece going up like that, v naught y. And my 50-degree angle is right there. Okay. What is v naught x going to be? 40 cosine 50. How'd you do that? I told you how. Is v naught x touching the 50-degree angle? Yes or no? Yes. So it's going to be cosine, right? What do we put in front of the cosine? The magnitude of that velocity. If the angle touches my horizontal component, it's going to be cosine. So what is the vertical component going to be? By process of elimination, sine, right? But we can see it's not touching the 50-degree angle, right? So we know that this is going to be equal to 40 sine 50 degrees. Touching, not touching comes in handy. You always write down the magnitude, in this case, which was 40, right? And then sine or cosine angle. And the sine or cosine is given by like what's touching, not touching. Okay? Most angles in projectile motion are measured from the horizontal. So your x will almost always be cosine, your y will almost always be sine. But that's going to start changing in chapters 5 and 6 and 7 and 8. So again, I want you right now thinking about it so that by the time we get to the harder stuff, it's a little bit more solidified in your brain. Okay, so these are things that I have now figured out, right? I've figured out V naught y, which is 40 sine 50 degrees. So I got to calculate that number. V naught x cosine. What am I doing over here? I'm making my list, aren't I? I got 30.6 meters per second in my calculator. If somebody else has a calculator, you can check me. 25.7 meters per second for the V naught x. Okay, yeah, we agreed? Okay, good. Sometimes I flip them because I can't read. All right, what else could be in my list of things I could know and not know? So acceleration, I can get the list from my toolbox, right? So have I written down a Vy yet? No. I wrote down a V naught y. I got V naught y, Ay, T, what else do I get? Delta y. Anything else? Oh yeah, okay, we get all the way through. Oh, delta x is a new one, right? V naught x and T. So we've got a delta x to add on here. We already have a t, and we already wrote down our V naught x. Okay? So I got my list of possible knowns and unknowns from my toolbox. My tools can only work with these things, so it's good to know whether or not we know these things. So do we know how fast the Ford Bronco is going when it strikes the water in the vertical direction? Thank you for saying that. It's totally wrong, okay? But I know a lot of people were thinking it. Will it eventually be 0? Sure. But when it strikes the water, is it moving? Yes. But when it strikes the water, is its acceleration negative g anymore? No. Why? Water, right? It's no longer just gravity. It's come into contact with the water. And so we can't say that the final velocity is 0. Final vertical velocity is 0, because it's not going to be. And by final, it's implied that we're talking about like right as it hits the water, in that instant before it touches the surface of the water, how fast is it going? Because after it touches the water, well, that's a chapter 9 problem, where we talk about what happens when things come and, collide and that sort of stuff. So we'll get there. So if it's not 0 there, where is the vertical velocity 0? Remember, that motion is a combination of a sideways motion and a vertical motion. Where's the only place that that ball is stopping vertically? At max height. For projectile motion, if you are telling the toolbox that your initial or final vertical velocity is 0, then you've told it, solve till max height, or start at max height. If you want to know the maximum height of this thing, what are you going to put in for the final vertical velocity? 0, right? Because the only place that the vertical velocity is 0 is at max height. Everywhere else is going to be non-zero. Now, careful, is the velocity, not just x, not just y, but the combination of x and y, is the velocity 0 at the top of the flight? No. Why not? It's also moving sideways. So Vx will be a number, but Vy will be 0. Do you see the danger there? You all walked into the room, most of you walked into the room with this idea in your head that, oh, when it hits the ground, it stops. Well, eventually it does. But that's not projectile motion anymore, is it? Okay? So, Get it out of your brain. I'm telling you directly what the bad water is, right? Okay? When is the vertical Vy velocity 0? At max height. And if your initial vertical velocity is 0, what just happened to the object? It was dropped. Because it started at its maximum height. And it's never going to get any higher than that. If you're sitting here right now going, wait a second, I had no idea what Mr. Balogh said. What are you going to do? You can throw your hand in the air and ask me right now. Or, if you're too shy, what time is it? 8:36. You can go to the YouTube, go to about 33 minutes into the video, you'll hear it again. But more importantly, you write down in your notes right now, Mr. Balogh did something with 0 and I didn't understand what was going on. I need to figure this out. Because I just spent like 4.5 minutes talking about it, right? Important or not? Mr. Balogh doesn't do anything important up here. Okay, that's good. All right. Tangent, but an important one. Let's see. Where was I? Okay, so I don't know. That was a long way around the idea of I don't know what the vertical velocity is. Okay, but important, really important. Do we know the acceleration in the y direction? Sure do. It's in free fall. Do we know how long it's been in the air since launch? Nope. Do we know how high the cliff is? As a matter of fact, we do, because I just failed to tell you that we were on the edge of a 75-meter high cliff. Okay. So do we know what delta y is? If we're going to talk about like the whole motion of the Ford Bronco, we do. What's delta y going to be when it ends up in the water? I heard it. I heard it. Say it louder. Negative 75. Why is it negative? It ends up lower than where it started, right? Doesn't matter where you put 0, it's going to be negative because it ends up displacing downwards. Now, is it going to go higher than 75 meters as a part of its flight? Yeah, right? We're launching it upward, so it hasn't gotten to max height yet. It'll eventually get there, but for the whole flight, the delta y is going to be negative 75 meters. And how important is that negative sign? Your life depends on it. Because I will come and kill you. If you don't. No. It's just that on an exam, Mr. Balogh, I did everything right. I just missed a minus sign. And I'd be like, no. You missed the minus sign. The master minus sign. The one minus sign to rule them all and in the darkness bind them in the land of Mordor where the shadows lie. Like it's important. Because if you don't put that minus sign on there, what are you telling the toolbox? Launch up, accelerate down, end up higher than you started. Don't be surprised if the toolbox comes back and says, well, now you're doing imaginary physics. I'm going to give you imaginary numbers. All right. Delta x. What is delta x? It's not just the position. It's a specific position. It's the horizontal distance. This would be delta x, right? A lot of people try to draw this one. Nah, I don't know what that is, right? It's the horizontal displacement, right? The vertical displacement is negative 75. Horizontal displacement is going to be whatever it is. We don't know. Whoops, we don't know what it is. So, all right. Have you noticed a profound lack of words in this problem? Do you notice how I haven't written down any words, right? You'll be given lots of words for your homework problems, but I want you to see, right, that quite often the universe gives us things and we kind of have to make up the word problem, right? To be even to kind of get any traction in it. I've been mostly visualizing here, and I haven't given your brain any information about what we're going to find, which is both frustrating and wonderful. So what are we going to find? Everything. Let's find everything we could possibly find. What's something we could find? What's something we would want to know maybe? Time. How long is the Ford Bronco in the air, right? How long does it take from the time we launch it to the time it hits the surface of the water? Great, we could find that. What else could we find? How far? Like horizontally it goes? Maximum height above the launch point or above the surface of the water? It's one other thing I can definitely think of, having to do with the imminent impact. How fast is it going when it strikes the surface of the water? If you were launching me, I'd kind of want to know. So, and I know you guys will have dreams, fantasies maybe, about launching me off of something. Okay, so let's go for it. Let's solve for the time of flight. By the way, this is the problem we're going to be doing tomorrow in lab. Not with Ford Broncos. Okay? But we will be doing this problem, which is why we're spending a lot of time. It's your first one, and we're doing it tomorrow, and so we'll spend a lot of time. Okay. So, what am I looking for? Time. Right? How am I going to find it? What's my strategy going to be? Which of these equations could I employ to find out how long the Ford Bronco's in the air? Why are you saying the second one? We don't know Vy. We don't know the final y velocity, right? And the final y velocity is in the first and the third, isn't it? But it's missing from the second. That's kind of a clue, isn't it? So, do we know delta y? Do we know v naught y? Do we know t? Do we know ay? So t is the only unknown thing that we've got.
Didn't you do the third one if you have the initial velocity, the acceleration, and...
Okay, all right. So does everybody agree that the second one could be done?
Yeah.
Okay. Third one. Third one doesn't have time in it. So I can't get time from it. But what could we do? Find the final velocity. And then do what? Use the first one to find the time? Now, it seems like a little bit more algebra, doesn't it?
It's less.
Why?
Because if you do the time first, you still have to find the final velocity.
This is quadratic in t, isn't it?
Yeah.
Okay? So using the second one means you got to use a quadratic equation, quadratic solver, whatever, right? In your calculator. Okay? But if we use the third and then the first, we can avoid doing a quadratic. This is totally personal preference. Okay? I won't grade you down either way. You do it right either way, great. You did good physics. I'll do both. And why am I going to do both? I mean, eventually I'm going to want to find everything, so I'm going to want to find. But more importantly, I want to check myself, right? I want to see if I'm getting consistent answers, right? Because I'm not satisfied with just one answer. I need to know that that answer is going to be correct. So let's do it both ways, okay? So I'm not going to write down in words my plan. You might want to initially, right? But my plan now is to use the second kinematic equation and solve it for t, but then also to use the third equation solve it for Vy, and then use the first equation and solve it for t. We'll do both ways. Okay? So let's conquer the quadratic first. Now, solving the second equation for t is always going to end up as quadratic, and for quadratic, I don't bother with symbols. I just put numbers in. It's just what I do. Deal with it. Negative 75 equals, and what's my v naught y? Ah, good. Go back to the list. Plus 30.6. Why did I put a plus in there? Because I wanted to tell future me that I thought about it. I wasn't blind and just throwing numbers in to see what sticks. Why is it positive? What way is the Ford Bronco going when it launches? Sideways and up. But we're not worried about sideways right now, right? We are only solving the vertical problem. And does it launch upwards initially? Yes. And what direction is up? Positive. I'm going to put a positive on things that are positive and put a negative on things that are negative. And then I'm going to write minus 4.9 t squared. Where'd that come from? It's negative 9.8 for the acceleration, right? And divide it by 2 gets you 4.9. All right. I'm going to manipulate this around to get it into a form that my math teacher yelled at me it had to be in. So there we go. There's my quadratic. And now, how do we solve quadratic equations? The internet. Now, of course, like on the internet, okay, on the exam, you're not going to have the internet, right? Okay, but let me show you how to do your homework quicker. Wolfram Alpha. You've heard of Wolfram Alpha? This is, have you heard of Mathematica or MATLAB? A little bit. These are programming languages that know all math everywhere all the time. And Wolfram Alpha is the website that has Mathematica on the back end. Wolfram's the company that made Mathematica. Anyway, it's like Google, but for math and science. Okay? And you can Google information and all that kind of stuff, get data. But more importantly, it can do math. Like, solve 4.9 t squared minus 30.6 t minus 75 equals 0 for t. T squared. Thank you. Get your syntax right. Now, if you know Mathematica's programming language, you could put it in math, but it also understands natural language inputs, right? It can do integrals. It can do derivatives. It can do all kinds of stuff, right? You don't have to pay for it. It'll say you need to pay for it, but you won't have to, okay? So I hit enter. Oh, okay. So first of all, it looks like it interpreted my typing correctly because I had AI correcting me. No, sorry, HI, human intelligence. Correcting me, right? Okay. It gave me, math. Okay, approximate form. There we go. Okay. You can always hit the approximate form. More digits. No, thank you. Okay. How far can we? So like you can ask Wolfram Alpha to calculate pi out to 10,000 digits. It'll do it for you. It'll probably say you have to pay me money because it'll take time. But anyway, okay. So that was, wow. Yeah, no, we don't, no, sig figs. Okay, right? And then it drew me a plot, which is kind of meaningless for the, anyway, right? So third derivative, no, I don't want, okay. No, all right, getting distracted. Notice that there are two answers here. I know you can't see it on the screen, but I'm just going to copy them down while I've got them right here. Negative 1.88 and 8.12 seconds. Okay, so there you go. Wolfram Alpha can solve it for you. Your calculator can solve it for you. Of course, you can have a calculator on the exam. If your calculator has a solver on it, you can use it. You just need to leave me a note that says I used my solver. right? If I see something written down and then all of a sudden I see a solution and no indication of how that solution happened, I'll just assume you're up to no good, right? You need to communicate what's happening and just say, in my calculator, okay? All right, so got the times. Which one do I pick? It's not just because it's positive, though. It's the bigger number, and I'm doing more of my parabola. I kind of talked about this a little bit ago, right? So I know the 8.1, because I can flip this around and get the math to work out so that it becomes positive 1.88 and negative 8.12. That shouldn't happen as long as you're defining down as negative and up as positive, but just be aware. So I'm going to pick this one and call it my time, right, for the time of flight. Okay, over to the purple. So let's see here. Vy is going to be equal to the square root of v naught y, 30.6 squared. Now I'm not going to put plus 30.6 on that one because I'm squaring it. Doesn't matter if it's plus or minus, what's it going to turn out to be? Positive answer. All right. Minus 2 times 9.8. Well, okay. I'm going too fast. Plus 2 times a negative 9.8 times a negative 7. I have a bad habit of moving all my minus signs out to the front as I go. Okay, so now I'm going to put this into my calculator. And I got 49. I can't read my own handwriting. I think I got 49. But since it's a square root, it's going to be plus or minus, isn't it? Okay. And this is where it becomes dangerous. Which one do you pick? Ask yourself the question. Which way is it going as it strikes the water? It's going down. So what are we going to pick? Negative, right? So our answer is negative 49 meters per second. And again, there's that minus sign coming to get you, because if you were to put positive 49 back into the first equation, do you think you might get the right time? No. How frustrated are you going to be about a minus sign in this class? Really frustrated, right? Learn now to always be interrogating your numbers. Should this number be positive? Should it be negative? And how do I know?
Why don't we also look for the x velocity?
We're going to get there. We're going to get there. We're just doing the vertical part right now to find the time. Okay. So now I stick that negative 49 up here. So Vy is going to be equal to V naught y plus 30.6 plus a negative 9.8 times a, what the heck am I doing? I don't know what I'm doing anymore. I got to solve this. I got to do some algebra first, Mr. Balogh. Do your algebra. Don't put numbers in. Vy minus V naught y equals AT. What happened there? I moved the V naught y over, and now I divide both sides by A to get my T, right? So T is going to be Vy, my final, which is negative 49, minus my positive initial 30.6, all over, and I'm now panicking because it looks like negative time, but in the bottom, it's negative 9.8. Which means all my negatives are going to go away, and I'm going to get a time of 8.12 seconds. So what does that tell me? My time appears to be correct, right? It appears that I checked my time, which means everything seems to have worked out. I probably set the problem up correctly, so on and so forth. It's my check. As a bonus, I've also gotten the final y velocity, right? So I can write some of this stuff in here, like this is negative 49 meters per second. My time of flight was 8.12 seconds, right? And now we can talk about delta x, right? Because to get how far it goes sideways, what do I need? I need to know how fast it's going sideways. And time. Do I have time now? I sure do. So I can now calculate my horizontal range, right? And that's going to be positive 25.7 times my time, 8.12. Everything's going in standard units, so I know I'm going to get meters out. I got 208.7 meters, or roughly 2 football fields away. It's pretty impressive. No real way to check that. Sometimes you just have to be confident in your ability to use your calculator. Have we found everything? We found everything in that list. But what about max height?
0.
Oh, we can throw zeros in now, right? So if we're going to solve this for max height, can you guys see the gray? Is it hard to see? Down here?
I think so.
Hard or easy? Hard?
I'd say hard.
Hard? I was hoping the new laser projectors would make the gray easier to see. Let's do, yeah, the contrast is not good. How about green? Is that better? Okay. Little tip for teaching, never use yellow on a white background. I've never understood yellow expo markers. Maybe they're for the abomination. Maybe the architects were secretly brilliant and knew that yellow markers were cheap. No, they're still dumb. Okay. So yeah, don't ever use... I'm sure they were smart and brilliant and had reasons, but they were all bad ones. Okay. What was I doing? For max height. For max height, we change the list a little bit. Because we're going to set V... What happened to my green? Vy, we're going to set to 0. So does that mean our time is 8.12 anymore? No. Time is no longer 8.12, because 8.12 is what? Time it takes from launch till it hits the water. Is that the same time as launch to max height? No. So this is kind of a different problem, right? But with Vy equal to 0, V naught y still equal to positive 30.6. Bad, Mr. Balogh didn't put signs up there. And now if I try to go solve for the time, what time will I get? It would be the time from launch to max height. You're telling the kinematic equations, you're giving it 0 for Vy. You're basically telling it to stop calculating there. So any times you get would be to max height, and more particularly any delta y's you get would be what? Difference between where it starts and where max height is vertically. So we don't know time. We want delta y, so this looks like a job for the third equation. Because there's no time in it. We could go find the time, right, and then use the second equation, but the third equation gets us there directly. So this is 30.6, this is a 0, and this is a minus 2 times 9.8 times the delta y. Solve that for delta y. I'm not going to do the algebra. And you get 47.8 meters. Okay. What is the 47.8 meters? Above the what? Launch point. Not above the water. It's above the launch point because we gave the kinematic equations information about launch. So the 47.8 is this vertical distance right here. So if the problem asks for how high above the water is the Ford Bronco at max height, what do you have to do? Got to add the 75. Just be sure like what Wiley Plus is asking you to find, right? We're good to go. All right, we found a whole bunch of information here. We didn't find out how fast it was going when it struck the water. Or did we? How fast is it going when it strikes the water? It's not negative 49 meters per second. Because that's not how fast it's going when it strikes the water. What is negative 49 meters per second? Be very precise. It's the y component of the velocity. 49, negative 40, I'm in green still. Negative 49 is the vertical component. What other speed does it have? The horizontal component of its motion, right? And what is that final x velocity? 25.7. Why?
Because it's the same, no acceleration.
It doesn't change. Right? No acceleration in the x direction means that this is 25.7. So when the problem asks for how fast is it going, what is the speed of the object? What are they talking about? Just x? Just y? Both. If they want to know the vertical component, they'll say, what's the vertical velocity when it strikes the water? What's the horizontal speed when it strikes the water, right? But if it just asks for how fast, if it just asks for speed, remember that we broke in two-dimensional motion up into two one-dimensional problems. And you got to stitch them back together. How do I stitch these two components back together? It's an x component and a y component, and we are looking for the hypotenuse. Pythagorean theorem, right? This will be the square root of 25.7 squared. Sorry, I'm writing so small. Plus 49 squared, right? And that gets me 55.3 meters per second. How full is your brain? How many things do you need to keep track of and check? A lot is the answer, right? And you probably didn't catch all of them the first time through. Is that safe to say? We've been at this for an hour. One problem, 1 hour. And that's with my help. How bad is chapter 4? Okay? Now, again, we're going to do this problem tomorrow in lab. Again, not with Ford Broncos. We're going to launch ball bearings. Okay? But we're going to do this problem in lab. And you are going to do the problem where you solve mathematically, but we're also going to measure the time of flight and how far horizontally things go. Right? And so hopefully tomorrow things will start to click. You'll make a lot of mistakes tomorrow. Nobody's going to get hurt. Okay? Not those kind of mistakes. But you're going to make math mistakes. You're going to make physics mistakes. Okay? And through those mistakes, you're going to learn all the things that you personally need to keep track of. I've tried to cover everything that everybody needs to keep track of. Right? But let's, before we finish off today, let's do a quiz. Okay? Let's do a quiz and see how well you are understanding what's going on here.